next talk is by Matt Williams. And Matt, I'm going to let you give us the title of your talk.
Sounds good. Thanks.
There you go.
Thank you. I appreciate it. Thanks to the organizers. This is really a fun workshop to participate in. So the title's a little bit long, and that's just because it mimics the paper. Bayesian dependent functional mixture estimation for area and time index data. And we're talking about an application to monthly county employment. I just want to take a moment to acknowledge my longtime collaborator, Terrance Savitsky, who is definitely the lead on this paper, but I did have some contributions, and since he's not here, I can embarrass him a little bit. And I usually tell everyone that he's the premier Bayesian statistician in the federal government, and I really believe it. So thanks again for the long-term collaboration. Today, we're gonna break it up into three sections here. Talk about the forecast, the data set, the local area unemployment survey forecasts, and then we'll talk about the different modeling components that we put together and it's actually how they work. And then we'll spend time looking at some plots to compare performance from different alternatives. So hopefully there'll be some time for questions, even if I slow down a little bit. So background, local area unemployment survey, the LAUS, and I'm sure that there's a savvier way to pronounce that, but that's okay. They publish county level unemployment and employment totals every month for every county and municipal civil division in the United States. So it's a huge undertaking. Terminology-wise, it's actually not a survey. And so what is it? Well, it's actually a projection forward from the census instrument, the quarterly census of employment wages. It's by 7 months, and each county time series is modeled or projected separately, and there is an adjustment for seasonality. So in principle, it's already working. It's already working well. But the idea is, can we improve on that by borrowing strength across similar counties? Can we simultaneously model the time series across counties and get better predictions? So it's kind of a tall order, but it's a really interesting problem. So just a little bit more background on the local area unemployment survey. It partners with the states to get the county level employment data. There is a current employment statistics program, but it's not available every month for many of the counties because they're small. So over half the counties it's not available for. So we're going to focus on just using the QCEW and projecting forward 7 months. In terms of dimensions of the data, we're talking about over 3,000 counties, and we're looking at about 15 years of data, 180 months. So we'll talk about the counties being indexed by I, the months being indexed by J. So for the comparisons we're looking at, we use the first 14 plus years to estimate and fit the model, and then the last 7 months we forecast or predict. Okay, so that's at a high level the motivation. Motivation, we have a program, operational needs, it's going well, but we think, conceptually there might be a way to improve it. So let's talk about the model components. So there's 4 main model components, and the first 3 we'll see here, the next one will pop up. So after we properly kind of scale or transform as needed, we're going to assume that the responses are normally distributed. And really the key is this mean function, this functional index by time and county. And we're going to break that up into 3 components, your sort of linear predictor, your trend, and your seasonality. And that's often, common decomposition. So a little bit more details on the linear predictor. I guess there's not a whole lot to say, except that we have various predictors, which I'll mention, and we have these regression coefficients and a prior distribution on them. So really where the action or the interest, what was new for me, started to come in is what we do with the trend. So we have a non-parametric smoother to identify the nonlinear trend, the drift, and that'll be set up with a bandwidth of 1 in autoregressive term. And so how that's formulated, it turns out to be this quadratic form in equation 1 and 2. So it turns out to be a normal distribution based on the lag differences. And it has a precision matrix Q. And the nice thing, if I could just take a quick aside of using a precision matrix, is if you insert structural zeros, that implies conditional independence between time points. Whereas if you use a variance covariance matrix and you have structural zeros, that implies the strict or full independence. So it's a little bit more flexible if you work on the precision matrix scale. Some technical details, this is technically a rank deficient formulation because the mean's not identified. So you can't get the mean just from this, you'll need the linear predictors. And another way to think about it is a probabilistic local smoother. So this will take some of the drift and other things out of the way. These first two components, the linear predictor, this trend function, you know, they might have been new to me, but they're pretty standard in the literature for functional estimation. So what's sort of new about this contribution is the next part, the seasonality part. And we actually have several options, and we will compare several options for accounting for seasonality. One is to go with a seasonal smoother. So this kind of a 12-month bandwidth rather than a 1-month bandwidth. And the formulations are similar, but in a technical sense, they're slightly different depending on if we have a proper distribution or improper distribution. And the difference is this rho I term. And we'll just, rather than going into a lot of the philosophical details, we'll just see how those differences shake out in the plots. You know, how one can capture some kinds of seasonality and the other can capture different kinds of seasonality. And finally, is kind of like our old school trigonometric basis function, Fourier basis function. I'm sure I get teased about mispronouncing that, but the idea is that you have a repeating pattern, say seasonality of 12 every 12 months. If you have 11 sines or cosines terms, you can reproduce any repeating function. It spans the basis, it spans any repeating function. So it's simple and efficient. So we thought, let's see if we can include that. The idea is we put that in the linear predictor term up top. Okay, so for counting, that's the 3 components. I said there'd be 4 components. So let's go to the 4th component. And this is sort of where the magic happens. And I have to defer to the paper because of the details. But the idea is that we collect the hyperparameters. So the mu, the delta, the phi, the nu or eta. And instead of each county really having unique values, or each county having the same value, we want to have something in between. We're in one extreme, we can't estimate it. In the other extreme, we're sort of borrowing information across counties that are unrelated. We want to have a reasonable amount of clusters of counties and have them pool information. So how do we do that? There's 2 ways we can do that. We could do it in sort of a non-supervised way, which is implemented through a Dirichlet process model, or we can do it in a supervised way, which uses what's called a dependent Dirichlet process. Again, I don't really have enough time to go into the details. The idea is that we can use predictors, covariates, to influence our clusters. And why is that important? Well, we talk about employment. There's a lot of good information available. So BLS has a location quotient, which is employment concentrations by economic sector compared to the national average. And those sectors are based on 2-digit NAICS. I realize I don't have that spelled out, North American Industry Classification System codes. And here's some examples: construction, transportation, etc. And the idea is for something like an economic time series, spatial adjacency doesn't really make sense. You know, you could have counties that are very different economic activity being adjacent to each other. So instead, we should use something like a location quotient. In addition, we also had access to unemployment insurance claims, excuse me, and some latitude and longitude. So these predictors, not only are they in the regular part of the model, but they're used to kind of prime the clustering, to have counties that are more likely to cluster together based on similar covariate values. I spent a little bit of time conceptually to set that up. Okay, so for the next step, we're just going to look at a bunch of plots. So hopefully that'll be useful to illustrate the differences between these models. So first, we're going to start with, again, this is one of the 3,000 plus counties. And this is where seasonality is less expressed. You know, it might be there, but it's not obvious. It's not just gonna hit you right between the eyes. So at the we see definitely that there's a drift, though. There is a nonlinear trend over time. And the far right here is the last 7 months that have been forecast. And we compare 3 different models. The legend is at the bottom here, the Fourier basis with this dependent clustering is the red or the pink, and it does a really good job. You can't really see the difference there. And it also has uncertainty intervals associated with that. Now we compare the 2 different seasonal smoothers I talked about, the blue and the green. I've got my cursor in the way. And what's happening for when seasonality is less expressed, this local one, this green one, is actually too sensitive to the previous 12 months. You see that it picked up on a spike at the bottom here, right ahead. So it's a little bit too sensitive for this kind of county, but the other one, the blue one, what we're calling the global one, seems to do okay. Okay, well, let's look at a different example. Let's look at an example where seasonality is more expressed. I mean, this you could almost just do by hand. You can almost just project out the next 7 months because seasonality is so strong. So what happens here? Again, the Fourier basis does well. It forecasts very well, and the intervals are pretty tight. The sort of local, what we're calling smoother, does well in this case because it's borrowing information mostly from last year. And the more global one is not doing so well because it's sort of averaged out what happened. So you see that it's kind of in the middle there. It's not tracking the seasonality. And this was the struggle that we had with these 2 methods. They were flexible, but depending on how strong the seasonality was expressed, they kind of flip-flop in terms of which one would do better. And that's why we landed eventually with the Fourier basis. So let's look at a couple more examples. Here, we're going to compare the 2 different kinds of clustering. So we're going to stick with the Fourier basis. And there's some seasonality, it's a little irregular. And we're going to compare the predictor-assisted one, where we use those covariates to inform the clustering, versus just an unsupervised clustering. And we see it makes a difference. This red, pink, pinkish color is tracking much better. It's forecasting much better than without. Okay, let's look at another example here. So that was a smaller county. And this is a larger county. Again, seasonality is definitely happening there, right? But it's a little bit irregular. And in this case, again, the predictor-assisted clustering does better than the sort of naive direct clustering. And another way to think about it is, we're not just trying to extrapolate the pattern from this county. We're also borrowing strength from similar counties that have been identified. So that's another way to think about why we're getting better forecasts, is that we're better able to cluster with like counties. And I guess one of the reasons why we're looking at a bunch of different sizes of counties is that, not all the program, like we said, the CES doesn't necessarily cover all the counties, particularly the smaller counties. Hope somebody will jump in to correct me if I misstated that. So we're looking at a variety of different behaviors. Here, we see a big jump, a few years back, and then it settles down. And so the idea is, well, does that have any kind of downstream influence on the model? It doesn't appear to be the case for these 2 models. The other models, it did. But again, this is just an example of the predictor-assisted clustering doing better in terms of forecasts unsupervised. Okay, so I had a little bit of time, so we threw in, again, in the paper, there's more details. I know it's a bit of a tease, so I apologize. But instead of having a time series approach where we borrow strength across space, you could also set up a spatial model approach where you have things evolve over time. And so we set up kind of a straw man, a little bit more complicated than that, spatial model. And that's what we're looking at now in the blue turquoise versus the Fourier basis predictor-assisted clustering model. And we see that the spatial model does okay, but it's definitely not performing as well, not forecasting as well as our time series-based model. So I've shown you a lot of plots quickly, and I'll spend a minute on a summary table. So what we're doing here is we're summarizing the different models that I talked about. So the top 2 are variations of using the trigonometric basis, the Fourier basis, The top one is what we think is performing the best because it uses the predictors to help with the clustering as opposed to the unsupervised clustering. And then we have two different more non-parametric smoothing or filtering for seasonality, also with the predictor assisted clustering. Then we have the spatial model. Then we have what's in production now. And so we have two columns. One is the root mean squared predicted, or I like to say forecasted error. And we see in general that the Fourier basis does better and the predictor assisted versions of clustering do better. The last column is based on a mean absolute prediction error, and it's something they use internally at BLS to evaluate the programs. And so we see that our proposed method also appears to do better than the production model method. Okay, so just to wrap up, in summary, I'm happy to provide the link to the Bayesian analysis is open, open publisher, so it should be available for everybody to see that. If not, feel free to send me a message. To summarize, heterogeneity between counties, heterogeneity between time series that we want to combine is actually a pretty tricky challenge for seasonal structures. It looks like the Fourier basis, because it's so efficient, even though it's a little bit less flexible than these autoregressive smoothers, because it's so efficient, it does a nice job helping us with the other terms in the model. The predictor assisted clustering, again, which I didn't have a lot of details going into, does better than the unsupervised clustering. We did it in such a way that it does appear to be better than modeling the time series separately. So hopefully that's not too surprising. And when we cluster, there's always tempting to cluster spatially, but when you cluster based on similar predictors, similar indices, that performs better than just latitude, longitude, and proximity. Okay, I want to stop and say special thanks. These are folks that worked with Terrance directly in various ways to help evaluate the work at BLS. So I just want to extend my gratitude to them. And so Garrett, Tyler, Nick, Andrew, Walter. I know there's other people here on the call who are involved as well, so thank you. And I just want to share our contact information. Again, Terrance is kind of the PI on this, but I had fun working together as well. And I'm happy to take questions if we have time. Thank you.